Welcome to EDU World Space.
In this question, we want to find the electric field due to a uniformly charged slab. So this charged slab extends along the YZ plane, and then it has a thickness of 2D. Okay. So it's D, here is minus D, and then 0 here. And then we want to, there are two parts in this question. First, we want to explain why the electric field is 0 at the x equals to 0 line at the center of the slab, and find the electric field everywhere. Okay, so in this question, for at x equals to 0 at the center of the slab, okay, it is symmetrical. This line is symmetrical. Or it's a line of symmetry. Yeah, it's a line of symmetry of the slab. Okay, and then we can treat that as if there are two uniformly charged sheets, slab being placed side by side at x equals to 0. Okay, so yeah, and then the electric field at x equals to 0 by each slab will be, okay, so the electric field by each slab is parallel to the x-axis. Okay, yeah, so you cannot point in y or z direction, okay, because it extends in the yz plane. Okay, yeah, then at x equals to 0, those electric field, okay, are equal in magnitude. Opposite in direction. Okay, and so at x equals to 0, the E is 0. Okay, so what I'm saying is that, so I'm treating this as like there are two slabs that are placed side by side at x equals to 0, and then slab 1 is generating a field pointing to the right, and slab 2 is pointing to the left, and then you just add these two up and along the x equals to 0 line, and then it will just give you 0 everywhere at x equals to 0. Okay, another way to say that it's just 0 by symmetry, yeah, it's kind of the same as saying that you are kind of treating this as two separate slabs. Okay, yeah. Right, so in part B, we want to find the electric field everywhere, and here we will be applying Gauss's law. Okay, so first we will do inside the slab. Okay, we will draw the slab here. Okay, enlarge it. Okay, so we have shown that the E is 0 at x equals to 0. So we can actually have our Gaussian surface that looks like this. Okay, so that on the x equals to 0 line, that phase is going to have E equals to 0, and we know that E is pointing like this. Okay, and it's going to be uniform because it's constant on the x equals to like x. Okay, so and here on the top and bottom face, you are going to have 0 flux. Okay, yeah. Okay, so using Gauss's law, okay, the surface integral of electric field across the Gaussian surface, okay, is equal to the charge enclosed divided by epsilon naught. Okay, so in the Gaussian surface, the charge enclosed is going to be rho times the A times the X. Okay, yeah, so the charge density times volume. Okay, so this is the charge density, and then this is the volume. Okay, so this gives us the charge enclosed, and then at the left hand side, we are only going to have E times A. Okay, because this is from the right surface. Okay, yeah, so this is equal to rho AX divided by epsilon naught. Okay, so E will be rho X divided by epsilon naught. Okay, so this is the inside, okay, the magnitude, and then the direction will be so E in, okay, will actually be rho X epsilon naught times X hat or I hat. Okay, okay, so if it's in the negative side, it will be pointing to the left. Positive side will be pointing to the right. So the vector form would just look like that. Okay. All right. So we want to do outside the slab. Okay. Draw the slab again. Okay. So the Gaussian surface will look something like this. Right. So using Gauss's law. Okay, so the surface integral of the electric field, A, which is the electric flux, and is equal to the charge enclosed divided by epsilon naught. In this case, the charge enclosed is equal to rho A times D, okay, because it's only this part. And then the left hand side, okay, E dot dA is just going to be E times A at the right surface. Okay, the flux through the right surface, and then the E field is again pointing to the right. Okay, and so we just equate both of them. E times A equals to rho AB divided by epsilon naught, and so E out will just be rho D over epsilon naught, right? And in the vector form, okay, it's equal to rho D over epsilon naught for x greater than d, and then minus rho d over epsilon naught I hat for x less than negative d. Okay, so this will be the expression for E out. Okay, so just to highlight the answer, this is E inside the slab, this is E outside the slab. Okay, and that's all for this question.